Hi, my name is Bonnie. I'm a semantic solutions graph specialist at Squirro, which is a Synaptica company. I am delighted to introduce Daniel Loup from Arup, a global collective of designers, engineers, and consultants that are dedicated to shaping a better built environment. Arup is at the forefront of using taxonomies, knowledge graphs, and semantic modeling to describe buildings and infrastructure in very rich detail, from entire properties all the way down to a wall socket. Daniel is a civil engineer specializing in water engineering with deep experience across Asia, the UK, in sustainable drainage and flood alleviation schemes. He's led the development of data-driven workflows for climate resilience, asset management, and building information modeling. As part of Arup's global taxonomy and ontology team, Daniel helps shape the best practices that provide technical guidance for their knowledge organization systems using Graphite tool. And tonight, he'll be sharing insights on his talk titled Taxonomy and Ontology Management for the Built and Natural Environment, Inter-Taxonomy Reconciliation for Consistency and Interoperability. So please join me in welcoming Daniel.
Hello, everyone. It's my pleasure to talk today about Arup's approach to taxonomy and ontology management for the built environment, built and natural environment, primarily focusing on the inter-taxonomy reconciliation for consistency and interoperability. So I'll start by sharing a brief overview of Arup's taxonomy journey, moving on to a few case studies related to BIM for buildings and infrastructure, and a closing view on Arup's taxonomy future ambitions. Firstly, a brief introduction to Arup as an organization. Arup was founded by Sir Ove Arup in 1946 and currently has over 19,000 people working worldwide from 94 offices, spread across 34 countries. Dedicated to sustainable development, Arup is a collective of designers, consultants, and experts working globally. Founded to be humane and excellent, we collaborate with our clients and partners using imagination, technology, and rigor to shape a better world, ultimately. And so first, our taxonomy journey. In order to use technology and rigor, Arup uses a variety of tools. And in doing so, that means that organizations such as clients, consultants, and contractors describe the same data in different ways across the tools that they use. Data quality management, including the cleansing, transforming, and exchanging data, is a costly process, and interacting with evolving taxonomies influences consistency and interoperability over time. So from a starting point to where we want to be, we're along this journey of reconciling taxonomies across various domains. And so to meet these business demands, the Arup identified the need for a global taxonomy register, and so Graphite, the taxonomy and ontology management software solution used by Arup, enables our next steps in this journey, and some of the key features that Graphite provides in enabling a multidisciplinary organization like Arup to manage a wide range of taxonomies and ontologies are shown here, that also enable Arup to comply with various industry data standards and also client-specific data standards. And so this is just a very high-level snapshot of overview of what's of our taxonomy and ontology management. To date, we have over 100 active users on Graphite, with over 50 internal and external taxonomies in active development, and some being consumed by applications that we use to deliver our services. And so I'll be talking later about a few of these taxonomies related to the case studies. And I myself am part of the Arup's Center of Excellence team for taxonomy and ontology management to support Arup's skills networks in shaping the best practice for governing their taxonomy and ontology data at different levels, either locally, regionally, or globally. So the first case study here is our Global Revit Standards. Revit is one of our core BIM platforms, used by over 5,000 staff members globally for over 2 million hours per year. And until recently, the Revit standards have been managed independently in each region, which makes sharing resources, automation routines, and data between projects very difficult. In addition to this, the data structures that were present in our Revit standards were locked into these proprietary files, which made us unable to reproduce them for use in other software. Previously managed in Excel, Python scripts convert the related tables to a RDF format. The data is serialized to a .n3 format text file chosen for conciseness, and the files were then added to Arup's Global Taxonomy Register on Graphite. So the building components are stored as concepts, allowing for Revit-specific attributes and settings to be expressed. Also, the concepts allow for relationships to various classifications and external definitions. Within the family scheme, this contains around 4,500 concepts, parenting around 6,750 family types, representative of the Revit building components and their parametric variations. The parameter scheme contains around 9,000 concepts describing well-defined primitive data properties outside of Revit's proprietary format. And so I'll move on to the second case study from our building envelopes skills network, where key objectives were to expand their existing taxonomy with meaningful semantic relationships to create a rich knowledge graph. And so this involved mining knowledge from existing documents to extract subjects, predicates, and objects, and form build an ontology. And so the key outcomes would be enhancing to be able to retrieve, manage, and process knowledge and project data more effectively, enhance consistency of the outcomes across regions and projects, and then also enable automated design and reporting processes to be implemented and maintained over time. And so this is a view of the predicates that of the concepts, over 5,000 concepts that were identified that enrich and fill the gaps of the uniclass taxonomy as a basis. And so once identifying concepts, building envelopes team will then mine for predicates, and with over, for example, with over 20,000 potential ontologies between two schemes alone, between materials and finishes. Not all of them are possible, relevant, or frequent, as shown by the example here. So a meaningful knowledge graph is expressed with relevant and weighted ontologies. This is a view of part of the manual collaborative approach that was adopted through workshops that were held amongst the main experts to identify the concepts and predicates, moving from a glossary to a taxonomy to a thesaurus to an ontology, with a few examples specific to the elements of a building envelope, for example. And here's a closer view of the relationships between physical components and their materials, for example, and their parameter sets that are then related to properties that may be calculated through analysis or defined in specifications. And so the final case study, which is related to our work with the Environment Agency in the UK, which is Arup's largest water client globally. Arup is currently delivering a wide range of flood and coastal erosion risk management projects under the EA's collaborative delivery framework, where the Environment Agency is one of the central government early adopters for interoperable built environment information management, using specified requirements and rules to drive efficiency and productivity. The EA mandates the production of data deliverables in accordance with the EA's exchange information requirements and their data requirements library, including 3D models, 2D drawings, and data exchange files such as geocopy files. And so ensuring the interoperability between the models and drawing and data exchange files is a major technical challenge across a project delivery, a project's life cycle, and also the assets life cycle. And so one of the data exchange deliverables is required under the EA CDF is geospatial construction operations building information exchange, otherwise known as geocopy file, which is a BIM data format and process standard. And so within the EA's data requirements library, a ontology for assets managed by the EA is defined, and this includes the attributes required for the assets and their elements within a GeoCobe file at the end of each project delivery stage. And here's just an overview of the distribution of attributes that are required, as you can see across each delivery stage, and how they're distributed between assets and elements, where there's, based on the most recent revision of the DRL, around 140 physical assets with 364 distinct element types. And as you can see, there's various formats of these attributes. And so to optimize the delivery of GeoCobe, this is a view of the Arup's data exchange workflow for GeoCobe, where with the taxonomy and ontology data hosted on Graphite, forming Arup's knowledge graph database. This data can then be linked to various processes along the workflow to first build the asset geometry, to form the asset model, to then push that data to a project database, and then from that project database, then map that data into a specific deliverable data format, where, for example, the GeoCobe data exchange file template is provided by the EA, and where they have similar Excel-based deliverable templates for whole life carbon assessments and safety, health, environmental, and well-being risk management data. And so this workflow has the potential to be replicated to feed into other data sets. And so in order to do this, it requires a taxonomy of each asset type, and the related modeling standards, and so how that physical asset would be, the elements that make up that asset, and then also the equivalent BIM object type that would represent that asset or element type. And so by using parametric modeling of the asset's geometry in Autodesk Civil 3D, for example, this enables automated computation of the asset properties, and also then the automated visualization of the geometry and extraction of asset properties, such as accurate surface extraction that can support the intelligent machine control earthworks construction, say for earthworks assets such as a flood defense embankment or vehicle access road, and also then volume extraction for cost and carbon calculations, which enhance the construction and procurement process. And so this data exchange workflow as shown earlier, linked to a reference data database of the taxonomies and ontologies, and it enables agile project delivery to consistently produce the high quality output over time that complies with the latest client and industry standards. And as you can see here, say with the publicly available EA data requirements library API that's provided to support supplier side automation, we're able to have a view of, for example, these shown here is the revision history of the DRL, and you can see it's becoming quite consistently updated, and we're able to then say update the EA DRL ontology, convert that into RDF format, ingest it into our global taxonomy register on Graphite, and then update our workflows, data exchange workflows if necessary, or validate that the certain processes are still aligned with the target output. And so I'll finish just with a view of the Arup's taxonomy future, where faced with the challenge of different standards, classifications, and naming conventions across projects, the goal would be to form a unified and structured taxonomy enabling data exchange and interoperability, aligning our local classifications to industry standards such as the Uniclass and GeoCOBE, and also standardizing terminology across models and disciplines. And as shown here, based on the various businesses, we can organize shared knowledge and objectives across a variety of businesses, say forming both human and machine readable structured knowledge between concepts such as physical assets, either built or natural, and their materials, the habitats they're related to, the carbon factors of those materials, the geography that they're situated in, the parameters associated with those assets, both existing or proposed new designs, and then also relate those parameters to concepts within local or regional or global frameworks such as the United Nations Sustainable Development Goals or the UN's Biodiversity Finance Initiative or Kunming Montreal Global Biodiversity Framework, which would all contribute to Arup's goal in shaping a better world and leading in sustainable development. So that's the end of the presentation. So thank you.